Laser-induced breakdown spectroscopy, or LIBS, is an analytical technique that's been used in laboratories for many years. Latest technological advances have made it possible to shrink LIBS into a handheld version. In theory, LIBS is capable of analyzing virtually any element in the periodic table. Today, most handheld LIBS analyzers are used for fast sorting of alloys in scrapyards and alloy identification and analysis in various applications within the metals industry. So, how does LIBS work? During LIBS analysis, a focused pulsed laser hits the sample, removing or ablating a very small amount of material from the surface. The sample is hit by thousands of pulses during a typical 1-second measurement. The ablated material is heated up to and exceeding 10,000 degrees Celsius. The temperature is so high that the atoms actually break up and form a plasma. Despite these high temperatures, the sample does not get hot to touch during the analysis and so can even be held in your hand safely during the measurement. So, what is actually happening within the atoms? When the high-power pulsed laser hits the sample, the electrons in atoms' outer shells are ejected. Because the electrons in the outer shells are shielded by the inner shell electrons, they are not so strongly drawn by the nucleus. This means that less energy is needed to eject the electrons from the outer shells. The ejected electrons create a vacancy, making the atom unstable. When the pulse stops, the plasma starts to cool and the vacancy is filled by electrons cascading down from the outer electron shells. The excess energy released when the electrons move between two energy levels or shells is emitted in the form of element-specific light. For a typical metallic sample containing iron, manganese, chromium, nickel, vanadium and so on, each element emits many wavelengths leading to a line-rich spectrum of up to thousands of peaks. The wavelengths of light are collected through a fiber optic cable and then processed by the spectrometer. Each element is associated with a specific spectral peak. The LIBS technique is virtually non-destructive. Following a LIBS analysis, the tiny burn spot left is so small it can be difficult to see with a bare eye. LIBS spectra are quite complex, with potentially hundreds or even thousands of lines for each element. The concentration of the element is calculated from the intensity of the spectrum peak. Then, an advanced algorithm is used to identify the sample type and calculate the concentrations. There are several reasons why people choose to use the handheld LIBS technique. It is the fastest analytical technology available today to identify and analyze metal alloys. It takes just 1 second to measure virtually any alloy, including aluminum alloys. That's up to 20 times faster than handheld XRF. A LIBS analyzer is very rugged because the detector is typically protected by sapphire glass, one of the hardest materials known today. This means that you can safely measure sharp and pointy objects, including turnings and shavings. It is also very easy to use, just point, shoot and read the result from the screen. From a regulatory and license point of view, much less is required from the user than, say, for XRF. Typically, no expensive licenses or time-consuming training classes are needed. However, it is important to check your local legislation concerning issues such as the use of the safety goggles. Oxford Instruments strongly recommends using safety goggles when operating a Class 3B laser device. LIBS is an excellent alloy identification tool which can also deliver good chemistry when required. If you want to know more about Oxford Instruments LIBS analyzers, visit our website.